Let's go ahead and get started. So today we're going to talk about backpropagation. Okay, we looked at the forward pass for neural networks last week, and now we're going to look at how we actually update our weights and biases by running backwards through the network, calculating derivatives. We haven't actually talked about sort of what the top level of the training loop looks like. So it looks kind of like this. We're going to have this neural network, and we're going to initialize the weights and the biases. Okay, and it's going to turn out it kind of matters how we do that initialization, but we're not going to get into that now. So we do the initialization, and then we're going to go through a number of epochs, right? An epoch is what? One what? One pass through the data, right, through all of our training instances. We're going to figure out how our weights and our biases should change. That is, what delta we should adjust them by. We'll just set that to 0 to begin with. And then we're going to go through and let's change this. Let's just set the delta and biases. So we're going to go through and get a mini batch from our data set. So a mini batch, how big is a mini batch? On the order? What's that? 10 to 100. Maybe if you have small inputs, it might be 1,000 or 10,000. It's probably not 1,000,000, and it's probably not 1. Okay? So you're going to get the mini batch. And these mini batches should be randomized across epochs, right? So we're getting a random mini batch without replacement. Okay? And it's going to give us our x's and our s's. And that's why I call it xs and ys. It's sort of Haskell-like for multiple here. So we have multiple x's and multiple y's. And we're going to do a forward pass on the x's. And that's going to give us predictions, right? Another name for predictions is, y hat. So these are our y hats. And then, in italics, in a manner we haven't yet described, we're going to calculate our gradient descent vector. So we're going to take our loss function, and we're going to take the derivative of that with respect to each of the weights and each of the biases. Okay? The loss function is going to take our y's and our y hats, and we'll then do this computation. Once we've figured out what the gradient descent vector is, we're going to multiply that by a learning rate, which is much less than 1. And we're going to subtract that from our existing weights and biases. So by subtracting it, we'll be going in the opposite direction of the gradient descent. So imagine we're blindfolded, and we're up in the hills. And we're trying to find our way down to the stream, or the stream, and we know that's at the bottom. Okay? What direction do we go? If we want to go down. Kind of feel in different directions and see which one, well, is not going up, is certainly a good start, right? But let's say you've got multiple directions that are going down. What would you prefer? The steepest one. So that's what we're going to do, right? That's our gradient descent. We're finding the gradient, and we're going to shoot down that gradient. And if we have a steep gradient, we'll go farther than if we had a shallow gradient. Right? A shallow gradient might mean we're sort of at the bottom of the bowl. So if it's a shallow gradient, we'll go slow, we'll go a small amount. If it's a large gradient, we'll go a high amount. But we'll always be going in that direction. And that's what we're doing here. So every time, every mini batch, we're basically getting a sampling of what the true gradient descent is. Right? Because we're getting a sampling from our total batch of instances. And our hope is that we're going in roughly the right direction. If we got a particularly bad batch, we may go in the wrong direction, but that'll be fixed with our future batches. Right? And every epoch, we might go through and check the validation, accuracy, and loss. Right? If the validation loss starts going up, what does that mean? So the validation loss goes down over some epochs and then starts going back up. Overfitting. So stop. Don't go so far. Okay? Or do something else to address overfitting. Does this idea make sense? We're going to look at some various ways of calculating this calculating this gradient descent vector. And in fact, one way is numerical differentiation. So let's say we've got this function, and we are trying to calculate the gradient of f with respect to, let's say, w1. So this shows that same computation, right? We've got a computation graph here where every primitive arithmetic operation has a node. So x1 times y1 is represented with the y, with the star here. x2 times w2. And by the way, these slides are now available. These and all previous slides are available on Piazza. There's a resource, and so this is a PDF, so don't feel you have to copy all this. You might just make a note where I make a correction, but that's all there. So then we add together the two multiplications plus the b, multiply by -1, take the exponent, take e to the whatever, add 1, and take 1 over x. And this gives us out f. Questions on that? Okay, so let's go ahead and look at the derivative, right? So the derivative of f with respect to w1, the partial derivative, I'm going to call that also f prime sub w1. So the sub w1 is with respect to 2. Right? Well, we can just define that as the limit as epsilon approaches 0 of f of x1, x2, w1 plus epsilon, w2 and b, minus f of x1, x2, w1, w2b, right? All over epsilon. We agree that's just the definition of the derivative. And so we can approximate that if we just say, well, let's just use a small epsilon, close to 0. Like, and this is a reasonable number, right? 0.000001. And so we can do that. So we just will plug in, let's say, here, our x1 is 3, our x2 is -2, our w1 is 1, our w2 is -2, and our b is 2. So we have to, of course, be looking at the gradient at a particular spot in the graph, right? So therefore, we have to know what our values of all those are. And so we get about 0.59. So we can say that our gradient is roughly 0.59. Why don't we just use this?
You have to calculate the function for every single, once for every single weight.
Exactly. You're going to have to do for every single weight. And basically, you're going to need from here all the way, here all the way. In the terms of our layers, we're going to have to be doing a lot of forward passes, right? Because we're going to have to recompute our forward pass with a slight modification, right? A slight epsilon. So it's just way too many computations. However, if you are implementing your own form of gradient descent, it'd be nice to double check what the gradient descent actually is. And this is a super easy way to check what the actual gradient descent is, right? You have your forward pass already, and you just need to calculate that with a slightly perturbed weight. Does that make sense? So we're going to use it for double checking. We're not using it for actual implementation. So what do we use for implementation? Oh, and let's just show numerical differentiation in Python. So here I have a notebook. With that same picture. And so how am I going to do differentiation? Well, I basically gave labels for each of the nodes. I called them A and C and D. I skipped B because we already used B. And just put in, actually I take it back here. Yeah. And then I just said F is equal to J of I, of H, of E, of D, of C. Maybe this isn't the easiest way to have read this. But F is equal to 0.73. I set epsilon to be what I said. I recalculate this using W1 plus epsilon. And then I get that df dw1 is 0.59. So that's how I got my 0.59. And to tell you the truth, the first time I did this, the first several times I did this, I usually use Google as my calculator. 1 over 1 plus e to the negative 42. And it usually works. Let's see. Okay, so all right, 1 plus 2 divided by 3. That works. Okay, so I was doing this all using this calculator, and it turns out to be very difficult to debug if you get something wrong, and there's a lot of parentheses to go wrong. So I found that Jupyter Lab was a much easier way to go.
Does splitting your function into its component parts do anything for the purposes of this derivative?
For this numerical differentiation, it does not. For what we're going to be doing later, there will be a reason we're doing that. Okay. So I could just as easily, and perhaps should have just written 1 over 1 plus e to the negative, or x, whatever. Okay. Backpropagation. So here's how backpropagations work. We implicitly have this computation graph. And what we're going to do is try and first do our forward pass. Okay, so our forward pass says we're trying to evaluate with these values of x1, w1, x2, w2, b. So we're going to go ahead and just assign them. Green is going to be our forward pass. So those are our values, and that's the value coming out of x1, right? So it's the value of x1. And now we'll do the calculation for what the node A is. So A is its incoming values are 3 and 1, so we multiply them together, we get 3. Okay? We can see how we get to our plus. Gives us a 1 times -1 is -1. E to the -1 is about 0.4 maybe, a third, 0.37, not bad. It's not like I've not seen these numbers before though. We add 1, 1.37, 1 over that is going to be 0.7, 3, very good. Okay, so F is equal to 0.73. Now when we're doing our derivatives, we're doing derivatives of what with respect to weights? What function are we interested in? Loss. It's our loss function. It's not our y hat, right? It's not our sigmoid at the end. It's our loss function, right? Because that's telling us how good we're doing. All right, so here's what we're going to do now. We're going to go backwards through here, calculating what the derivatives are at each step, what the gradients are. So we have f of j. Right? This is the node j, and this is the node f. Is there any difference between j and f? Because the value of j is what's coming out of this arrow, and that says that goes to f. So f of j is just j. So the derivative, f prime, with respect to j, I'm not going to put the with respect to here, is just 1. Wow, this is very fancy. So that says that df dj is 1. So we'll write that in red underneath. So far, I hope so good. Now we need to look at j prime of I. Right? We know j of I equals what? Right? So I'm looking at this j as both the name of the node and also kind of looking at it as a function. Right? So it's a function that takes its input and does a 1 over x. So j of I equals 1 over x. Sorry, j of I equals 1 over I. So j prime of I equals -1 over I squared. Right? Great. But we don't want j prime of I, right? We want df di, or that is f prime with respect to I. This is what we want to calculate. How do we get that? The chain rule says we can use f prime with respect to j times j prime with respect to I. Okay? So we take f prime with respect to j. Well, what's that? We just calculated it as 1, right? It's whatever we just wrote here, times j prime with respect to I of 1.37, so of this value. So we're going to take -1 over 1.37 squared. We get a 0.53. Does that make sense? Okay? It's, again, backpropagation is just lots of applications of the chain rule. All right. I of h is h plus 1, so the derivative is 1. So what do we think is going to go here? Negative 0.53, because it's going to be this derivative times the derivative of this, which is 1, right? Of this evaluated here. But we don't care about the evaluation because it's constant. I don't know what just happened. All right. H of e is, you can see why I didn't put e to the e here, because e would be overloaded. So x of e. So h prime of e is x of e. Okay. So we're going to be, if we're calculating f prime with respect to e, so if we're calculating f prime with respect to e, then we want f prime h, which is 0.53, and then j prime negative 1, right? So e to the negative 1, which is negative 0.2. All right, then we have some basically negative 1. So we're going to multiply this by negative 1. And then, right, we have multiple variables here in this function. And so d prime with respect to a is 1. What's d prime with respect to b? 1. And d prime with respect to c is 1 as well. Okay, what is a prime with respect to w1? x1, right? So I don't know why I wrote this one this way. So although this is true, this is not the equation we want, because we're not interested in the gradient for x1, right? x1 we don't get to change. It's an input value. We are trying to look at w1. So, oh, well, I wrote it down. That's good. All right, so it's going to be 0.20 times 3, which, based on the rounding, is 0.59. And then we get similar values for these. Let me just bring it back at the very end and ask whether you have any questions. And perhaps as a better motivation, imagine that you were having to do this on an assignment that would be handed out on Wednesday. Would you have any questions on this? Yeah.
You mentioned the term gradient descent.
Yes.
Like a more power definition?
Gradient descent just means you're at some particular spot on a function, find the gradient, that is the derivatives, with respect to every coordinate, and go that direction. That's it. So in particular, sorry, let's say here I am. I'm in this three-dimensional space, and I calculate the gradient, and it's curved. You just can't see too much, but I'm up high. And so I'll calculate the gradient with respect to x1, with this direction, and I'll calculate the gradient with respect to this direction. And then I will take the vector, compose to both of those, and say that's the direction I go. So if I'm, I don't know, 3 steep here and 1 steep here, then I'm going to go mostly this way and a little this way. Okay. This can be a little tedious to do, which is why you want to write code for it. One other thing you can do is work at slightly higher levels. So rather than doing pluses, plus 1s and times -1 and e to the whatever, do something like x1 plus w1, x2 plus w2, sum them together, and then just take the sigmoid, because we know, right, 1 over 1 plus e to the negative x is the sigmoid. Do we agree that I'll calculate the same thing? Right, the sigmoid is just taking over the 1 over 1 plus e to the negative x. And we can go ahead and do our calculations, and we get a 0.73 out, which is a good thing. And now we go backwards, and we get a 1. And now the question is, what is the derivative of the sigmoid? And it's the sigmoid times 1 minus the sigmoid. Okay? So 0.73 times 1 minus 0.73 is 0.2, and then we work our way back. So this can make life a little simpler and easier.
So here, your loss function is just, yeah.
We don't, our loss function is y hat, right, if we looked at it. We don't have, what we are looking at right now is how to do this backpropagation for any function. We will be applying it to loss function. It just made it larger, and it was a large enough example. Okay, so we get the same values. Let's go look back at here. So I defined these functions, which exactly match, right, the labels here. So for instance, h of e is x of e, I of h is h plus 1, and so on. And so for our backpropagation, well, for the forward propagation, right, the forward pass, I just went through and calculated for every one of them. You know, a out is a of x1, w1. Because we can't have a function with the same name as the variable, I called it a out as the output of the function a. And the good news is, of course, we come up with a 0.73. So the backpropagation, what we'll do is we're going to define for every function its derivative. So dA dw1 is x1. Let's see. E of d equals negative d, so dE dd is negative 1. J of I is 1 over I, so dJ di is negative 1 over I squared. Okay? And then we just kind of go ahead and calculate df di, then df dh, then df de and d and c and a, just working our way through. And at each point, so let's look. So df dc, for example, is df dd, whatever that was, times the function dd dc applied to C out. We just work our way through. So it was important that we saved all these. And that's in fact what has to happen on the forward pass, is you have to save the results so that you can then go back, because you're wanting to compute the gradient at basically each node for the chain rule. Does that make sense? All right, so. I want to be in Keynote. There we go. All right. This is still a real pain. This is how backpropagation used to be done, is people would basically define their function and then define the inverse. Not the inverse, the derivative, and then go ahead and apply those. But it's not very fun. So here's what's done. Automatic differentiation. So well, let me describe this first. We're going to go through on a forward pass, and we're going to identify which nodes we want gradients for. So in this case, we want gradients for the two weights and the bias. Okay? And then, as we go through the forward pass, we're going to go through, as we compute A, we're going to say, A, we are going to need a gradient. Why are we going to need a gradient for A? Because the only way we're going to be able to calculate the gradient for W, given that we're making an operation on W, is if we have the gradient for A. So if any of your inputs require a gradient, you require a gradient. Okay? But we are saying here we're never going to ask for the gradient with respect to x1 or x2. So it's not going to bother saving anything there. But it is going to save for A. And the other thing we're going to do is immediately we are going to compute, we're going to create a function that computes the gradient. So it's going to take x1 times something else that's going to be incoming later. So incoming later, we're going to have the gradient for here. We just don't have it yet. But we know enough to know whatever it is, we'll multiply it by our derivative. And we know the derivative, because we're doing multiplication, and because x sub I is because we know we're doing multiplication, we know what the derivative is. Okay? So we're going to be creating this backward computation graph. So we're going to go ahead and now for the next one, compute another multiplication. And then for our plus, let's figure out what we're going to do here. So what will the, we're creating a red node, and it's times 1. This is really just, it's an identity function, right? Because of the fact that, remember when we had d is equal to a plus b plus c, that dd dA was equal to 1, and dd dB was equal to 1, and ddc is equal to 1. So we're going to take outputs to each of those, to the 2 multiplication nodes and directly to b. And that says that whatever the gradient is coming into this node, it's the same gradient that's going out to these nodes. And you see that gradient is going to get multiplied by 3 correctly to get W1. And now the times -1, we're going to have a times -1 because that's a derivative. We will output to the previous gradient node. And now for e to the x, that's going to be a little trickier, right? Because the derivative is e to the x. So do we have a value e to the x? Well, actually, this is e to the x. So we want to take, the output of this is going to go into here, and the input is going to be, we want to multiply e to the x times whatever the gradient is here. So we already have an e to the x, so we just take it. And then the +1, right, the derivative, again, is just equal to 1. So we just have an identity again. The 1 over x is a 1 over x squared, -1 over x squared. And what's our input to -1 over x squared going to be? Right here. It's the thing that was doing a 1 over x. This is the 1 over x squared there. And now that we're done with our forward pass, we saved all this information as we were computing our backward paths. And now we can go ahead and just evaluate our computation graph going backwards. And that will then give us gradients for every one of the things we ask for a gradient for. Okay, this seems like a pain. And so it'd be nice if, sorry, let's go our backward pass. So we just go through. I wish there were a simpler way to do this. There probably is, I just don't know what it is. So we just move back, apply the operators as we get them. So here is going to be what, -0.53 times, yeah, 0.37 coming out. We work our way back, and we get the same values we got before. So what does PyTorch do? PyTorch helps you by doing this automatic differentiation. So here's what you do. You create a tensor. What's a tensor? Did you say three-dimensional? How about we just say n-dimensional, right? So an extension of a point, if you're at a point and you go 90 degrees and you go to here, what do you end up with? A line. And then you take a line and you go 90 degrees and you get, let's say in the same amount, you get a square, right? And then you go 90 degrees from that out, and that volume is a cube, and then you go out 90 degrees out, and you get hypercube. And if you go out again from there, you get a hypercube. Well, no, you just get a hypercube of whatever dimensions. Same thing for tensors. All those things, all of those points, lines, squares, cubes, are all hypercubes, just of a lower dimension. Same thing for tensors. A vector is a tensor. A matrix is a tensor. A three-dimensional matrix is a tensor. A four-dimensional matrix is a tensor. What about a single value? That's a tensor. Yep. And I guess you could even maybe go down from there and say nothing is a tensor too, but we won't go there. All right, so we have these tensors. You can say for a tensor, I want a gradient. Okay. In PyTorch 0.4, which is the current version, that's true. In versions prior to 0.4, you actually had to wrap a tensor with a variable, and it's variables that you get gradients for. So PyTorch 0.4 is nicer. Why do we care about PyTorch 0.3? Because our FastAI library uses 0.3. So if you're using Jupyter Notebook, you're going to be using 0.3. So that's why I want to just mention that. Okay. So what happens is, as you are executing PyTorch operations, and this is really, this one I'm going to, this is a question mark. I think that's actually not true. It's actually just PyTorch operations. So what happens is PyTorch operations execute. It's looking and seeing, are the inputs to those operations, did any of them require a gradient? And if not, it just does its thing. And if so, it saves the information, decides it needs to have a gradient of this operation, and again, just sort of saves that, so later on you can find gradients. So it saves the incoming tensors, and then augments this tensor with an appropriate derivative. And since there are only so many PyTorch operations, all of them there have their derivatives predefined. Okay? In many cases, in CUDA, right? So it's going to operate very quickly. And then a gradient computation, you do reverse computation of the gradient of some final tensor, right? You did a bunch of calculations on tensors, and what do you end up with? A tensor, right? Even if it's a single numeric value, it's still a tensor. And so then you say, I want the derivative with respect to that tensor. Normally what we want is the loss function. The loss function returns us a tensor. It's normally going to be a single real value, but that is a tensor, and it's wrapped in a PyTorch tensor. So what we'll say is, okay, I want the gradient of that loss. Let's look at how that works. Okay, so using PyTorch, all right, so I've defined, right, just a function, f of x1, x2, w1, w2, take a weighted sum, and then return 1 over 1 plus ytorch.exp. I can't use math.exp because weighted sum is actually not a number. It's a tensor. Okay? We can see here, x1 is a tensor with 3 in it, 3.0. You could do multiple nestings here to show higher dimensions. So this is just a one-dimensional tensor. It's a one-dimensional tensor with one value in it. Right? We can have one-dimensional tensor with n values if we wanted, but we have one. We're wrapping it with the word variable because we're using PyTorch 0.3. If we weren't, we would just say it's a tensor. W1 we want a gradient for. So we take our created tensor, wrap it with a variable, and adding that we want a gradient. In PyTorch 0.4, you would just add the requires gradient to the tensor constructor. And we do the same thing for x2, w2, and v. We calculate. So now that we've got these tensors, we can calculate with them. So this is multiplying two tensors, adding a tensor. This is a particular torch operation to take the exponent, and we return 1 over that. And that gives us our result. So result is a tensor. Given that we know what these tensors are, how big is this tensor? How many elements in it? Because we're doing w1x1 plus w2x2 plus b exponent, or negate exponent 1. And so it's going to be only one element there. And then what we do is we say, OK, we want the derivative with respect to that result, with respect to f. So we're going to ask to go backward from here. And that's really key. From where is it you are trying to get the gradient? Because we calculated tons and tons of tensors, right? The weighted sum was a tensor. The torch.x was a tensor. Maybe we wanted the derivative with respect to that. But no, we want the derivative with respect to here. Okay. And what we would normally do is we'd calculate a loss function and then say, OK, loss dot backward. And then once you've gone backward, every tensor which requires a gradient has now a gradient field, a grade field. And so when we run this, we get that f is a variable containing this tensor. And then df dw1 is 0.5898, df dw2 0.3932, df db 0.1966. Does that make sense? It's really nice, right? There are methods to clear out the tensors. Sorry, to clear out the gradients. So actually, as you're going through your training loop, after you do your forward pass, you're going to call backward on your loss function. You're going to pull out the gradients. And then you need to clear the gradients so that when you go again, it is starting from 0. Yeah.
Why wouldn't it clean automatically if you calculated the new f, like another forward pass and then go back?
It doesn't, there's nothing that says I am a forward pass.
Okay.
There's just computations on tensors are a forward pass. And so you can either just turn off calculating gradients or you can reset them. But there's nothing exactly like you're talking about. Okay. So if you're doing a forward pass for your validation set, do you want to be computing gradients? Right? For your validation set, no. Right? You are just trying to see how good your loss is and what your accuracy is. So to speed it up, you're going to turn off gradient computation there. But if you don't zero out your gradients, then your new gradients are going to be on top of whatever your old ones are, which is not what you want. Okay, to make clear, we can actually using tensors here. So let's look at matrix multiplication. Let's say we're going to define a sigmoid layer. This sounds suspiciously like a neural network. With a W, an X, and a B. And we're going to do a matrix multiply of W transpose and X plus B. And then take the sigmoid of that. Right, where sigmoid is just that same 1 over 1x to the negative whatever. I'm giving you a ReLU layer even though we're not using it here because, I don't know, maybe that'll be useful for your next assignment. So just to show you what the ReLU looks like, we're going to, again, do the same matrix multiply in addition, but we're going to call ReLU. And ReLU, here we need a PyTorch way of computing ReLU. All right. NumPy has a way to do that. Torch, of course, has a built-in ReLU we could use, but I wanted to show how to do it yourself. So here, there's just a clamp method you can use. So the clamp says for every one of the values in the tensor, make it at least 0. Not hard to write the derivative for this, right? Clamp can also clamp on the other end if you use a max. We don't need that for ReLU, but it exists. So what do? We create x is a tensor. Notice the brackets here, right? We have multiple braces. Its shape is 2, 1. I highly recommend you keep track of shapes. Okay? So by shape, I just mean it's 2 by 1. W is also 2 by 1. And B is a single value. So here, A1 is our sigmoid layer of XWB. If we wanted to have another sigmoid layer, we could say A2 equals sigmoid layer of A1, comma, some new W in B. And then we could print the gradients. And we get the same values, except actually, what's the gradient with respect to dW? Because W is a tensor with more than one element in it, right? So that means the gradient is also a tensor with more than one value in it. Right, where we've got here, this is basically W1 and W2, the gradients. Does that make sense? Okay. So as you're doing your assignment, if you remember last week, we talked about how you could go through and vectorize the, here we're vectorizing a layer. This is exactly the vectorizing a layer. Okay, we could have had multiple neurons and weights for that layer, and we would have used the same code. We would have just initialized the W differently and the B. We could also, remember, vectorize across multiple instances, across multiple x's. And there we just set up a capital, we set up, I'm going to back up a second. We looked at 2 kinds of vectorizing. One was vectorizing for a given layer. And there we used a capital W. This is not using the capital W. So the capital W, actually, we took the weights and transformed them and then stacked them on top of each other. Okay. And then we said for multiple instances, we can stack the x's. Your assignment, you're going to actually have multiple neurons per layer. So you're going to probably do, when you're doing, if you want to do with PyTorch, you will want to do that vectorized implementation. Okay. Questions? Yeah.
So you can't use any NumPy operations on the tensor objects? They don't work?
You cannot use NumPy operations. You have to use PyTorch operations for which there are equivalents to most of them.
So like, if using Torch, like, you just can't use any NumPy at all?
Well, there are 2 things. One is NumPy objects are not the same as tensors. So if you have a tensor, NumPy doesn't even know what it is to deal with it. So that is one problem. You could do some computations in the NumPy world as long as you don't need to differentiate them. So if you need to do some computations there, you can, and you can convert a NumPy array to a tensor, a PyTorch tensor. Does that explain that? Okay. Other questions? Right. So this is just to recap, except second. So I'm going to make this same. Okay. Okay, we'll just do that. So an alternative we could have done is we could have set our deltas here to 0, and we could keep adding Okay, I take it back. Yes, what I had was correct. That is what I want. So what we are doing is, my indentation is getting me, it's a second. We are updating our weights and biases for every mini batch. Therefore, there's no reason to initialize it to 0 first, and there's no reason to add to what's there. Okay. If we were to move our updating weights and biases to after the for loop, that is only update it once every epoch, the good news is it'd be the exact gradient, right? Because we would have looked at every single instance and got the exact gradient. The bad news is, for most of the epoch, we'd be using very old weights. And only once we had updated it would we start from a better spot in our loss function. So by moving it over time, we're going to be quicker. So calculating the gradient descent vector, how could we calculate the gradient descent vector? There's some different ways. One way we could calculate it is we could go through for each weight and bias, tweak it by adding an epsilon, calculate our new loss function, and then take our new minus the original divided by epsilon. That part's pretty important. So that's one way you can calculate a gradient descent vector. Terribly expensive. Great for debugging your other gradient descent vector code. Faster calculation would be to just use dj/dw. That is, have some symbolic, some other way to calculate what that is. And that's what we're doing by having PyTorch do that for us. All right, questions? All right, let's look at how you can compute your gradients layer by layer in your neural network. Okay, so we want to compute the error at the last layer. And this is a repeat of part of what I talked about last week. But we're defining delta. What do the brackets mean? Yeah, last layer. So capital L means last layer, and the brackets means whatever you're talking about is with respect to the last layer, or for the last layer. So delta sub L is the error of the loss function with respect to our weighted sum. And then, if we have that loss, we can look at the loss for the previous layer. Okay. And if we have a bias at a particular layer, then we want to find the derivative of our loss function with respect to that particular bias given the loss for that layer. And then finally, a weight. Okay, so if we can do all this, then we're able to do our gradient descent and find our weights and our partial derivatives for every one of our weights and biases. So the last layer, we have, right, what does the last layer look like? We have a z, we have a equals g of z, right? And we may have multiple of these. And these all feed into some sort of an L, our loss function, which actually we're calling J. So we're saying, what is delta of L sub J mean? Right? It's the loss for the jth neuron the derivative of J with respect to Z. And using the chain rule, that's J with respect to G times G prime of Z. Is that a hard thing to calculate? Do we know what the derivative is of J with respect to A? We'd have to, where would we find that? What that derivative is? Say that again? Yeah, you'd have to look at the loss function. You'd have to look at, well, what's J equals, you know, J of, let's call this y hat, comma y, perhaps, right? Equals some function. We can determine what J prime is with respect to y hat. And y hat could very well be just the output of this if we had one neuron. How do we find this derivative? Yeah, we look what G is. We only have a certain set of them. We predefine what their derivatives are. And where do we get this value? Z of J. That's this input, that's this incoming Z, right? Which we have stored. So this one is not hard to do. And it's not hard to do in parallel. Okay. So that we can do it for all of the neurons on the last layer at once. Layer L minus 1 given layer L. Well, to calculate the error at layer L minus 1, we multiply W. What does W look like? W to the square bracket lowercase l, right? Let's just look at what this means. This is layer what? Layer L, and we have a bunch of weights. So here we have W L1 transpose, W L2 transpose, all the way down. Right, so we've got the weights for every, so these are all the weights for, what does this row represent? Say that again? Yeah, so this is neuron 1 in layer L, neuron 2 in layer L, and we're transposing them because we need them transposed anyway, right? Because remember when we're looking at computing for a given W and X, or W and activation, it was W transpose times the other. Right? And then here are our activations for the previous layer. What's this operation? Yeah, this was an element-wise multiply. And then we multiply the derivative times the incoming z's. So let's look at it. Let's look at a picture. So let's say this is layer L, and this is layer L minus 1. If we look at a weight on one of these edges, like let's say here, that W, let's just say it's 3. What layer is this actually in, that weight? It's actually over here, right? It's in layer L. So what we're saying is we're taking the weight times the error here, times the derivative here, and pushing it back. Very similar to what we were doing when we were doing our small backpropagation. And then we're multiplying that by our activation function times our incoming z's, right? So if we've got low activations at layer L, back up a second, if we got low gradients at layer L, what does it say about layer L minus 1? So if we have a, in fact, let's make it even better. If we have a tiny gradient, at layer L, that's going to tend to make the gradients at layer L minus 1 small as well, right? Any ones that get affected by it. And similarly, if you have a tiny activation, a tiny weighted input, you're going to also get a tiny gradient. Or if you have a giant gradient at level L, you're going to have a giant gradient at level L minus 1. And similarly, if you have a giant weighted input. So it's a problem if your gradients start getting too big or too small. We have a problem what's called exploding or vanishing gradients. Let's say the average gradient is 0.5, and we have a network that is 30 deep. Well, so we have a gradient of 0.5 here, and then we may be going down to 0.25, down to 0.125, down to where, as we're getting farther and farther, I guess actually from your position it's this way, right? Here's our last layer, and we move back and back and back and back. As we get to the first layers, our gradient's so small we're not learning anything, right? So this problem of exploding and vanishing gradients was one of the things that had to be solved in order to successfully train deep networks. And we're going to look at normalization as a way to deal with that. All right, what else do we have? At a bias, it's really pretty simple, because if we think about it, the derivative of, right, z is equal to wx plus b. So dz db is equal to 1. So that's where we get our 1 here. We just take the error for the weighted sum, and that is the error for the bias.
Are all of these gradients we're looking at in the backpropagation perspective? I'm just trying to get like the big picture of like what are these gradients we're looking at? These are the ones that we do in the backpropagation.
These are the ones we're calculating via backpropagation. Yes. So conceptually, how we get it, we don't particularly care about. But the way we are defining these, one layer based on the next layer, is because we're going backwards. Because really, that's the only way to do it, is to go backwards. And then finally, the error at a given weight is just, so let's try and interpret this. These are the incoming activations. And these are the, let's call it outgoing error. So the gradient for a weight depends on how big the things are that are coming in to the neuron and what sort of gradient we have into that weighted sum. Okay. Questions? All right, I think I'm going to stop here for this and ask whether there are any questions about the assignment 1 and how many people, if any, have successfully finished it. Okay, good news. For the rest of you, I will be in my office only until 2 today, but I will be there, and the Gruder's there tonight and tomorrow night if you have any questions. I'm trying to be responsive on Piazza, but are people having problems like just sort of running things? I would imagine it's the vast amount of your work getting the directory structure. Was that sort of the hard part of it? And how many people did it with Python, setting up the directory structure? And how many people are doing that with Shell? Okay, either one's fine. Whatever you're most comfortable with is fine. And I guess I forgot to ask you as well, how many of you are familiar with like the Unix command line? Okay, a few somewhat. So here's the deal. 2 things any computer scientist, computer programmer should know. 1, how to touch type, because you will be typing a lot. Okay? Are there anyone here who does not touch type, like using all 9 fingers? All right. So unfortunately, right, the time I used to give a talk at Google, like optimizing your life, optimizing your engineering life in particular. And one of the ones was, I was surprised at how many people would use 2 fingers to type. And you spend a lot of time typing both code and prose. And their argument was, well, it's too late, I never learned. Well, it's not quite true. It's not like there's this special moment in your life where you're well-tuned to be able to learn to type. Right? It's not like acquiring a language where, it's a lot easier when you're younger. So anyway, I would tell them all they have to learn to type. But the other thing you need to know how to do is use Unix commands, because you're going to be using them forever. I was realizing yesterday, I started using Unix like about 1980 and learned VI, or what was called VI back then, which was brand spanking new, in like 83 maybe. And so then I stopped for a number of years. I did Macintosh programming, and then I came back in like 15 years later, 10 years later, and it turns out my fingers still knew VI, which is really nice. So it's hard to believe that we are still using something that I've been using for 35 years, right? It's just crazy that is still state of the art. But it turns out it is. And for a while, it kind of went away, right? And Windows was where everything was at. And then it's funny now how for programmers, like Windows machine's not that important. You try and get some new software, and it's like maybe available on Windows. But yeah, it's available on Linux, and it's available on Mac. And that's nice to finally have. So you probably don't have to go through and do what I did, right? I read the basically documentation for the shell. You would actually be well served by reading the documentation for Bash. You would be very well served by learning a text editor intimately, either Vim or Emacs. Are there any Emacs users here? Okay, good. Let's just use Vim then. And the way to learn Vim is run Vim Tutor. Okay, Vim Tutor, all one word, and it will teach you how to do it. And you just need to kind of keep track of things and force yourself to do things the Vim way, not use your arrow keys. Well, first off, you should never use arrow keys. in Vim? What should you use? Yeah, is it HJKNL? I don't know. My fingers know it. I don't know it. So that's how you use to move around, because they're always there because you're on your home screen. So learn Vim, learn Unix. At the time I was learning Unix, there were probably fewer commands, and we had printed manuals. And so I just went through and looked at every single, like every command there was. What is it? Kind of what does it do, and so on. And then later I could say, I remember there's a way to do, there was some command to do something like that. So the first time I got exposed to Unix was in a linguistics class I took, computational linguistics. So we were required to take a certain number of liberal arts classes, and I found computational linguistics was one hack, and another one was logic in the philosophy department, which also was a nice hack. But anyway, in computational linguistics, we learned a special linguistics programming language called Snowball, which was very good at string processing. And we were given the assignment to print a reverse alphabetical dictionary. So if you had the words like ant, cat, dog, what else? So you would first sort by the last letter. So dog would be first, because G was first. And then you'd sort by the next to last letter. So therefore, cat would be next. And then ant. Does that make sense? So we were using Unix to be able to run this Snowball language. And somehow we'd already been taught about pipes, right, to feed the output of one program and the input of next. And we'd also heard about sort. And so I thought to myself, well, okay, if we take sort, it'd be handy not to have to write my own sort. And so basically, if we had a way to reverse every word, so feed this into a reverse, and then sort that, and then feed it into a reverse again, that'd get you back to this. And so I wrote a one-line Snowball program that would reverse words, maybe it was 2 or 3 lines, and then said, well, and you just run it like this. And thank goodness my professor didn't say, you're trying to avoid all the real work that was there. It's like, yes, you found the good way to do it, which is don't write much code. So but the only way you know about these is know how to run Unix and put stuff together. All right, any questions?
This is somewhat unrelated to Unix, but I was having trouble finding any documentation on FastAI and its library. Does that exist?
So here's what I would say. My one-word answer would be no. And 2-word answer would be not really. So I would like to come up with a FastAI reference card at least to describe the things that are most commonly used. Yeah. But no, there's not. So FastAI tries to do things the PyTorch way, but as I was trying to do like just a very simple network with PyTorch or with FastAI, I ran into, it just has some expectations of how things are for the particular, it especially does image manipulation a lot. And so no, but it will try to come up with something. Any other questions? All right, see you on Wednesday.